Thank you, Linda. Thank you very much for the introduction and a very warm good evening to all of you. And welcome to this session, ISP webinar session on Isolator technology and its innovation in aseptic processing application. So before I start, some few points. This session is going to be for a period of 1 hour 30 minutes, and I'll be completing the complete presentation for you. And after this, we'll be having a question answer session, which will be attended from my side. 1 minute. It is a subject matter expert team. I have got two people today, and the first person is Andrea, and the second person is Eric, who have got more than 10 years experience in isolator technology, in the designing as well as in the validation of the isolators. And they will be, answering all the questions which will be coming in the last 15-20 minutes of the question answer session. So if you have any question during the presentation, maybe it's like during the further slides, which I'm going to show, this particular part will be made very clear, because this is going to be a presentation wherein we'll be starting with what is an isolator, how it is designed, what are the regulatory requirements, and then we will also be talking about, the VPHP cycle as well as the validation requirement. So whatever questions that you will be having during the session, as Linda said, you can send it on the chat. You can also ask in person. That will be after the presentation is completed. So with this, let me start with the presentation. So the major agenda for this particular presentation is, first, we are going to talk about a pharmaceutical isolator definition, its regulations, how to design an isolator. So the designing of an isolator, what are the different components of an isolator, which makes a complete integrated line. We will also be talking about washing place and the VPHP decontamination. I think everyone will be very curious to know about. And the last part of this particular session is going to be about how to validate an isolator. So with this, let me start with the first part, which is a brief introduction and the definition part. So what is an isolator? What do you mean by a pharmaceutical isolator? So there are a lot of definitions which are available. ISP has got a definition. There is a definition coming in from PICS, which is there on your screen. There is a definition coming in from the PDA. And all these definitions, they talk about an isolator as an arrangement of physical barrier that integrated to the extent that isolator can be sealed in order to carry out a routine leak test based on the pressure to meet with the specified limits. It also provides internally with the workspace, which will be separated completely from the surrounding environment, and the manipulations which can be carried out inside space without compromising on its integrity. So this is a definition which is coming in from the PICS, and you can also see the definition coming from an PDA. There is one definition which I want you to understand completely, and that definition says that it is a contained decontaminated environment meeting with grade A or ISO 5 conditions used for the aseptic processing that provides an uncompromised continuous isolation of its interior from the external environment. So isolator technology, if you see, it gives you assurance in terms of the stability. So all the definitions finally are coming to one particular point, and the key points are: it is a contained decontaminated environment. You're going to decontaminate using vapor hydrogen peroxide. It is going to be completely sealed, so it will be leak tested, and it provides a continuous isolation of its interior from the external surrounding or the external environment. So it's a localized environment created by a sealed enclosure to isolate the product from contamination and or from the people. There is a definition also coming in from EU GMP, which says that it's a decontaminated unit. So everybody is talking about the same thing. It's like a decontaminated unit wherein, the internal is separated out from the external environment. it gives a lot of assurance in terms of, the sterility assurance. So there are two types of isolators. There are two types of isolator system. The first one is called as the closed isolator system that excludes the external contamination of the isolator's interior by accomplishing the material transfer, which will be through a aseptic connection, and that will be, not compromise any of the sterility part. So normally this type of closed interior system isolators you can see in sterility isolators, which is like a single chamber wherein you get everything which is pre-sterilized. You're going to hang it inside the sterility test chamber, and then you'll be going for the VPHP as the leak test, and then you will be, starting with the sterility. There are other types of isolators which are called as open isolators, which are designed to allow the continuous or the semi-continuous ingress and ingress of the material. So there is a material coming in inside the isolator chamber, and there is also material which is going to go out into another chamber. So it's like a continuous processing isolator, which normally you see when you are going to actually work for a vial filling line, which is an integrated vial filling line with an isolator. And it will also be like a PFS lines, wherein, there will be different chambers for the debagging or for the D-liner, and then it will be going to the main filling station. So we are talking about integrating different chambers of an isolator without compromising on the sterility part. So how the aseptic process evolution started? So when we look at the aseptic process evolution, basically in year 1930s, you can see that, they used to have a high tension electric cables on top. And basically, they used to do all the aseptic manipulations below that particular high tension cable. There were no laminar airflow modules, but these high tension cables at that particular time were used as a laminar airflow module. The filling process went on in year 1960s and 1970s. You can see this is how the filling process used to happen. And somewhere in 1970s, we had the systems wherein the entire ceiling of the filling room was made of or a fan filter unit. So basically, when we are talking about a fan filter unit, in that fan filter unit, the entire ceiling was of HEPA filters, and the equipment used to be placed below that. And as you can see, there was wraps which are like plastic curtains surrounding the operators. And this was the beginning for what we call it as an open wraps system. So here, though there was a laminar on top and it was giving a laminarity, but you can see that the operators are very, very close to the critical processing zones. And this type of system continued till 1980s. And then in 1980s or in early 1990s, I will say, the system for the isolation or the isolator started getting developed. So first, the isolator technology was used in the sterility testing isolators, wherein with the success of the sterility testing isolators and with the reduction in the positive controls, which, we used to have a lot of intervention or the manipulations done before the isolator technology came in. And with the isolator, there was more of the sterility assurance, and this isolator, which they initially developed for the sterility testing, slowly it came for the other production activities like the vial filling lines, the ampule filling lines, the PFS, and this is where the isolator technology started developing. Today we can see the isolator technology wherein we have two types of isolators. We have aseptic processing isolators and the aseptic containment isolators. So there will be question coming in on the screen. So what is the difference? What is the differential pressure of pharmaceutical isolators you have known? So this is a question for the audience. Okay, so can we have the answers coming on the screen?
We'll just give everyone a chance to vote. Okay, now it's on.
So yes, there is a positive pressure isolators and negative pressure isolators. So yes, both type of isolators, they exist. And basically that has been used for the different formulations that we are, having in this particular isolator activities. Some of the components or some of the compounds which are in powder form and they are very potent, they are categorized as OEB level 4 or OEB level 5 and in a powder form, normally are handled in a negative pressure isolators. But most common isolator that has been used in the pharmaceutical application is the positive pressure isolators. And if we can see the screen on which you can see two types of processing units, with the help of my mouse, I will just try to explain what is the difference between these two. So as you can see, it's an aseptic processing isolator. There is no product which is of OEB level 4 or OEB level 5, wherein it is called as a very potent product which is handled in the isolator. So normally when it's a very potent product, you have to take care of the operators who are going to be working outside the isolator zone, as well as you have to take care of the air, because the air inside the isolator is going to get exhausted to the outside environment. And when you are handling the potent product inside the isolator, you have to take precautions of not contaminating the environment outside. So basically, there are a series of BIBO filters which will be there for the containment isolators. But when we talk about the aseptic processing isolator, as it is not going to handle any potent compound, which is going to be harmful for the human as well as for the external environment, we do not have the bag in, bag out type of HEPA filters in the exhaust duct. So that will be a major difference between these two. And you can see that, in this particular chamber, this is the valve filling line. And in this, you have certain areas for the manual intervention, wherein the interventions are done through the glove port. And here, basically, there will be certain risers which will be going, because it is a potent and it's a contamination control isolator. It will be having above the false ceiling a BIBO or a bag in, bag out filter, which will, first filter the return air coming through the return risers. And then this particular air will be exhausted to the outside atmosphere. Okay. So as I was talking about the aseptic regime for the aseptic isolator, this is a picture which will make the things very clear in terms of the circulation and the exhaust of air. So as this particular part is going to be for the aseptic isolator, you have the main AHU chamber wherein the air is taken from outside. It will be first passing through a G4 filter, followed by the cooling coil, the blower, the heating coil. Then it will be coming to a final filter. In AHU design, you can have this as F9 with H13 combination, so that you can have even one more HEPA in the plenum, and there will also be HEPA filters in the terminal. So this will give you more protection in terms of the filtration of air, which is going to come through the AHU system. When the air is getting exhausted, it is getting exhausted through the exhaust unit, which will be taking the air to the exhaust unit. and the exhaust unit will have a catalyst filter. Now, why this catalyst filter? This catalyst filter is going to totally deactivate the vapor hydrogen peroxide, which is going to get exhausted, because normally when you do the VHP sterilization of the chamber, there will be an evacuation cycle wherein the air will be evacuated through the chamber and it will be going to the exhaust and it will be exhausted out. So if during the time of exhaust, we put the catalyst filter, which will deactivate the vapor hydrogen peroxide, so we do not contaminate the outside environment. So you can see in the picture on the right hand side, this is where your false sealing of your clean room area is going to end. So maybe in the normal case, this will again depend upon the size of the isolator. This will again depend upon, what type of isolator that you will be going for, what type of line. Generally, you will be having a false sealing in the clean room, which will be at around between 2.7 to 3 meter. And above that, you will be having a walkable false sealing, wherein you will be installing all the ducting, which will be getting connected to your air handling units as well as to your exhaust unit. When we talk about aseptic and containment isolator, so this is an isolator where we are going to handle OEB level 4 and OEB level 5 products, which are potent in nature and they have to be handled in a contained way. So the scheme changes over here. The air handling unit remains the same. You can have the same type of configuration for the air which is going to come inside the chamber. The air which is going to get exhausted will be passing through a BIBO or will be passing through a bag-in, bag-out filter, which is a HEPA filter. Totally, it is in a sealed chamber. The air will get first filtered if there is any contamination or there is any potent molecules present in the return air which is going through this particular BIBO. It will get filtered and then the air will be exhausted through the exhaust unit. So in order to have more assurance in terms of nothing gets exhausted to the outside environment which contains the potent compound, we also have a second police filter, which we call it as a police filter, which will be installed in the exhaust unit. So there will be one BIBO or one H13 or H14 filter, which is an absolute 0.3 micron filter in the BIBO. And there will be one more police filter in case there is something, some integrity failure happening for this filter. There is another filter of H13, H14, which is also installed in the exhaust. So you have an assurance that the air which is exhausted out will not contain any potent material in that. If you have seen the isolator right from 1980, in the initial stages, there were very few installation of isolators because they were very expensive. It's like the companies were going in for the rigid access barrier system or the RAPs, and they were trying to, make the system in order to have a proper separation between the operator and the critical work areas. Now, with the isolator technology being more matured, and basically you have a lot of options available with the isolator, and they are not as expensive as they were like 20 or 30 years back. More and more companies are going in for an isolators for the products which are even non-potent. They are like aseptically manufactured, but they want to have more amount of assurance in terms of handling these products. So over a period of time, we have seen the isolator market has started having more and more sale coming in for the isolators, which are for the compounding isolators, for the dispensing sampling isolators, the sterility test isolators, and even for the filling lines like vial, PFS, ampules. We have seen more and more companies going in for the isolator technology. They prefer to go in for the isolator technology with all the modern things that has been, developed along with the isolators. So this is a, a slide wherein you can see from year 2022 to year 2030, the annual growth rate for the isolator is going to be around 11.1%. So you can see that, a lot of isolators will be, replacing the current wrap system, what you will be having in your factories, and more companies will be going for the isolator technology. So this is one more slide which talks about, the ORAP, CRAPs and isolator, which is almost like 47.8% of the market. So today with the ORAPs, CRAPs is nothing but the closed wrap. It's like an isolator. But only thing is that in CRAPs, you do not do the VPHP as well as the leak testing. So it is much better than the ORAPs or the open wraps. But in terms of an isolator, it is little bit on the lower side. So you can see that around 47.8% is the market trend for the barrier isolator system. So for the barrier isolator system, you have passive ORAPs, you have active ORAPs, and you have an isolator. So what is the difference between these three? So basically, when you look at the passive ORAPs, it is a HEPA filter sealing, or it is a sealing wherein it's a FFU, a fan filter unit, which is covering the complete sealing of your aseptic or a sterile area. And the equipment is placed under that with the help of maybe the curtains or the plastic curtains, which acts as a barrier between a person and the critical working zone. But still, this is not a foolproof system, because the person can definitely go very close to the critical areas, thereby compromising on the stability part. In case of an active ORAPs, we have a laminar airflow module which is installed above the machine, and the machine is completely closed from all sides with the help of a polycarbonate sheets or the glass, which will be having the glove ports integrated. There will be doors for this, and basically, as we talk about a laminarity, wherein there is a laminar, and as this is not a completely a closed system, the air which is going to come from the laminar will be having, the laminarity, and it will be entering back into the room, that is into the background area. So in case of an active ORAPs, you will be taking the air from the room and you will be circulating the room within the machine with the help of the blowers and the HEPA filters, which will be giving you the laminarity. When we talk about the isolator system, I always say it's a room within a room. So it's a room which is completely sealed from the outside environment. And basically here, all the interventions that you do will be done through the glove port, and you will be having a complete sanitization of this particular isolators using vapor hydrogen peroxide, which will give you a 6-log endotoxin reduction. So normally in the active ORAPs also we use the disinfectants and we are doing the manual cleaning with that, where you may get around 2 to 3 log reduction depending upon the area that you are going to reach. And it is totally dependent on the operator who are going to do the cleaning. So the validation of this is going to be extremely difficult for you to prove. Whereas when you're talking about an isolator, which is VHP sterilized, basically, then you will be having a uniform, 6-log endotoxin reduction in all the chamber, because this complete process is going to be completely validated. So there is a question coming on your screen now. So what type of barrier or isolator are you using in your respective plants? So are you having a ORAPS or a CRAPS or isolator or a containment isolator? So we mean to say sterility isolators and a sterility and a containment isolators. So what type of, the barrier or the isolator system that you are using in your current plant? Okay. Okay. Yes. So I can see that it's like almost 60% of the people who are attending this particular webinar, they are working with an isolator. And there are other technologies like ORAPs, CRAPs, and even containment isolator. So great, fine. So let's move on. So what is the difference between the ORAPs when we compare it against an isolator? What are the major differences that are going to be there? So the first difference when we are talking about ORAPs, your surrounding or the background area is grade B, because ORAP system is open wrap. So it's like, the air which is going to come in the critical zone, this air is going to come back into the room. So it's not a completely a sealed or a completely a insulated system. And that is the reason when you are having equipment integrated with an ORAPs, you will have to have a background area of grade B. Against that, when you look at an isolator, the isolator can be leak tested. It is VPHP sterilized. So basically, when we are having a machine with an isolator, you can have a background area of ISO 7 or ISO 8. It's a big advantage. Normally, when we look at the initial CapEx investment, you will find that, the isolator lines are going to be more expensive compared to the ORAPS line. And this is normally how the comparison is done. Has anyone seen basically what are the benefits that you will be having year on year in terms of your working capital? Because when we talk about the difference between a grade B and a grade C, we are mainly talking about the viable and the non-viable monitoring. So what type of viable and non-viable monitoring that you conduct on a daily basis when your batch is going on in the machine for the grade B area, and what will be the grade B and grade C area? The difference will be the reduction in your environmental monitoring, which is viable and non-viable that you conduct. Second thing is, when we talk about a grade B, we are talking about the number of air changes. So normally for the aseptic area, as we want a sweeping efficiency or a sweep efficiency, which we calculate, less than 15 minutes, we should achieve the same class or the original class of the room when the last person and the equipment stops functioning. Here we are going to have the number of air changes. We are going to be more than 55 air changes or 60 air changes for the grade B area. So the more the number of air changes, there is more the capacity for the blower. There is more quantity of air which is going to come into the room. The major load for any of the pharmaceutical factory is the chiller, because basically this chiller is going to cool down the air below the dew point when the moisture gets removed, and then with the help of a blower, it will be passing on to the heating coil, where you will be doing the conditioning of the temperature, which is 23 plus minus 2, which is normally the case, which is there in the aseptic areas. So here with the grade C, you can go for a lower number of air changes, which are 40 to 45 air changes. So again, there will be year and year on saving that you will be having on the operational cost when you talk about, the ORAPs and the isolator. So maybe in the initial stage, the CapEx amount is going to be what is going to be higher than the ORAPs. But maybe over a period of time, if you have a good production output, then you will be able to recover the cost. And it's like any machine that you install in your facility normally runs for 20 to 25 years. So year on year, you can have the benefits of this particular operational cost saving. In terms of differential pressure, it's an air overspill without a defined differential pressure to achieve aerodynamic separation, which is the case in case of ORAPs. But in case of an isolator, you'll be having a controlled differential pressure with respect to the surrounding environment. So normally in the isolator, you have an overpressure. And that overpressure is maintained with the help of a dedicated AHU, which is going to cater to this isolator area. And generally, this overpressure is at least 15 to 20 Pascal more than your surrounding area. In case of air tightness, you cannot have the air tightness is ORAPs. But wherein in case of an isolator, you can have 1 to 3% volume per hour, the leak rate, which you can define and which you can even confirm, validate, before the start of the operation. The temperature and humidity in case of ORAPs is going to be dependent on your background area. So when you're going to have, say, suppose I just give an example, when you're going to have a cold chain product being manufactured in an ORAPs, you always have a buffer tank, which is 3 liters or 5 liters, which is feeding to the manifold, which is feeding to the pumps and then coming to the needle. Now, if your surrounding area temperature is 23 plus minus 2 and you are filling a cold chain product, which is 2 to 8 degrees. So you will be having this buffer tank getting connected to the clean room chiller in order to keep, or in order to fill the liquid at 2 to 8 degrees. What will happen is because of this temperature difference, there will be a lot of sweating on your vessels. There will be a lot of sweating on your pipes, because you will never be able to control the temperature and the humidity inside the ORAPs area. Whereas in case of isolator, you are going to go with the AHU, a dedicated AHU, which is completely a dedicated AHU for your isolator. You can set in your temperature, humidity requirements based on the requirements that are going to be for the product. So normally, when you are having a cold chain product, you can reduce the temperature, you can adjust the humidity in order to avoid the sweating happening during the filling activity. So you'll be having a much better control because there will be an overpressure, there will be a filtered air coming in, which is with the dedicated AHU. You can control your temperature, you can control your humidity. So you can work as per the requirement of your product. It will be having a lower sterility assurance when we talk about the ORAPs. As I said, this is going to be cleaned manually. And it's like whenever you try to, whatever disinfectants that you are going to use, basically you have to consistently prove that all the operators will be, having the same type of concept for cleaning, and they will be, cleaning all the nook and corner of this particular ORAPs. So, which is very, very, very difficult to monitor and validate. Whereas in case of an isolator, it's not operator dependent. So basically it's a vapor hydrogen peroxide, the cycle which you are going to run, the cycle which you are going to validate, and the cycle is going to give you an assurance of a 6-log endotoxin production. As you can see, basically when we talk about ORAPs and isolator, for the ORAP system, as the background area is going to be grade B, you'll have to have compulsory a sterile garment. You'll have to don the sterile garment. And when you talk about the sterile garments, there are other things like, the operator validation, the validation of your dress, wherein you do the swab test just to check whether, your dress, whether it is going to, spread any contamination inside the sterile area. But when you have an isolator system, you don't require a complete sterile gowning because your background area is going to be ISO 7 or ISO 8 in classification. In terms of containment application, you will find that in ORAPs, you cannot have, the potent product being manufactured, which will get totally contained inside because it's an open system. So basically, if there is any liquid which gets, drained due to the vial breaking inside the machine, if more number of vials are going to break, this liquid definitely from the base plate, it's going to leak into the background area. Whereas in case of an isolator, it's a completely a closed system. So you'll be having a containment inside isolated zone. So with this question coming on your screen, so what is the cleanliness requirement of the clean room ORAPs located? So what type of cleanliness requirements you will be having for ORAPs equipment? So I think during my presentation, I already said that, but still we'll wait for the final answer to come on the screen. Yes, absolutely. So it is grade B. So the background area for ORAPs, the equipments which are enclosed in ORAPs, a mandatory requirement of grade B for such type of areas. Okay, now we move on. Okay. In case of the changeovers, it's very easy for doing the changeovers when you are working with the ORAP systems. In case of isolators, you'll be having a longer campaigns for changeovers, but of course, there will be a lower risk of contamination. In fact, even for the isolators, it has been demonstrated that the changeover can happen within 50 to 55 minutes. Because nowadays, the systems wherein the changeover means you'll have to use a lot of tools for doing the changeovers. You have the tool-less changeovers wherein there are dome nuts assembly, which you can easily dismantle and you can change over from one size to another size. In terms of operations and interventions, yes, the operators can intervene. The doors can rarely, it can be opened. Yes, but yes, it can be opened. It's like, and once you are having a door opening, then basically nowadays you are going to have even the extended laminar for the doors. You are going to have the audit trails wherein, all the door openings are going to get recorded. And then you will have to give, the CAPA or the corrective and preventive action, why you wanted to open a door, why it was necessary. It is not going to be easy with the current regulatory requirements. In case of an isolator, you cannot open the doors. You cannot do any interventions by opening the door. So it's like a completely a sealed system. All the interventions that you are going to do in the isolator zone, they are going to be with the help of a glove boot. So qualification, it is less qualification compared to an isolator. And basically in terms of integration, the integration for the ORAPs is going to be easy design, and it's a retrofit which can be possible even for the older machines. You can do the retrofit, and you can also have a ORAPs for the machines which are old. But in case of an isolator, you require a specially designed base frame for the machine, and it is not possible for you to have any retrofit because it's a complex integration with process machines, not only in terms of mechanical, but also in terms of the controls. So now we come to the second part, which is the regulations. And in the regulation part, you can see that when we are talking about LF curtains, or we talk about, the curtains which are surrounding with the help of plastic sheets versus ORAPs and versus isolator, you will find that the isolator has got a lowest risk of any human intervention. And basically that will give you more of a sterility assurance compared to the ORAPs as well as to the LF curtains. As per the international regulatory requirements, Operators have direct access to critical areas when we're talking about the ORAPs. The surrounding is grade B. The routine application is sporicidal agents and non-suitable for a very high potent products. Whereas in case of an isolator, the operators do not have any direct access. The surrounding is grade C or grade D or ISO 7 or ISO 8. It is completely validated and integrated with the decontamination system, vapor hydrogen peroxide, and it is very suitable for a high potent product manufacturing. So what are the different regulatory requirements talking of? When we look at cGMP draft annex, it talks about the use of appropriate technologies, restricted access barrier systems, isolator robotic systems should be considered to increase the protection of the product. So basically, all the regulators are talking about having a stringent control as to how we are going to do the manipulations in the critical zone where the product is exposed, wherein the isolator system is found to have a much better control in terms of the safety. One is to the safety of the operator and even for the safety of the product. So we have another question coming on the screen. So what type of metal materials are used or required in isolator or in ORAPs? So what will be the material of construction when we are talking about an isolator and a ORAP system? So this definitely is talking about the inner chamber of the isolator or the inner chamber of the ORAPs. Okay. Of course, yes. 77% of the audience, they have given SS316L, and that is right. So when you have the inner chamber of the isolator or the inner chamber of the ORAPs, it is SS316L that is the material that has been used. So okay, we move on. So as per the international regulatory requirement for the containment control strategy, it refers to the filtered air that has not been interrupted by items such as operators with the potential to add contamination to the air prior to reaching the critical zones. So what are the critical zones that we have? If we look at the pictures which have been given, they are of vial filling line. So the critical zone is a zone where the vial is exposed basically. And this will be after the tunnel sterilization when it comes on the 10 table. From that point till the time the vial is capped completely, sealed completely. So it is always, you have to protect under the laminar. We call it as the critical zone till the time the vials have been completely sealed, capped. So when we talk about the filtered air that has not been interrupted, that means we should have a unidirectional laminar airflow module with a velocity of 0.45 meters per second, plus minus 20%. So nowadays we are also measuring the velocity, which is at the working height as per the cGMP. And we are saying that it should not be less than 0.36 meter per second to 0.45 meter per second. So we are measuring not only at the grill level, 6 inches from the grill, that is from the laminar, that is from the HEPA filters, but we are also measuring at the critical working height where the product is exposed. So when you have an isolator, you have your independent air handling unit where there is a pressure, there is a differential pressure against the room. There is a laminarity. The air is taken back through a separate channel, which are the return ducts, and you will be able to maintain much better control in the critical areas where the product is exposed. So you'll be having a much better protection again when we are talking about the isolator technology. It talks about the decontamination process using microbial decontamination of the interior, which you are doing also for the ORAPs, but of course it cannot be validated. But when we are talking about the isolator technology, here basically we are talking about, the complete cleaning or the sanitization of the chamber having a 6-log endotoxin reduction, and that can be validated and it can be, proved after one batch, after another batch. So it is like reproducible. So when we are talking about the international regulatory expectation for the material transfers, it talks about properly operated and maintained rigid transfer ports for the effective transfer of the material. Pass-through units must not compromise the isolation via ingress. So basically here we are talking about the pass boxes which are there for the stability test isolator, through which the material is transferred inside the chamber of the stability test isolators. And by designing this pass boxes, we should not compromise on the isolation. Sufficient overpressure should be supplied and monitored continuously at a mouse hole location. So here when we are talking about a complete integrated vial filling line, basically from the filling zone, the vials will go to the conveyor, which will carry them to the lyophilizer, to the row by row feeding system, or through the AGV. Unloading of the lyophilizer, the vials will be going to the capping machine, and all these transfers are going to happen through different chambers of the isolator. So here we have to have a proper overpressure maintained so that we have a proper pressure for all the different zones of the isolator. Decontamination, it is full exposure to all pre-cleaned surfaces. It must render the inner surfaces free of any viable contamination. 6-log reduction of BIs for VHP decontamination. The material testing is recommended. We are going to test the BIs. We are also going to expose the CIs, which are the chemical indicators. Breach of isolator integrity should lead to the decontamination, and product contact equipment, that is a stopper hoppers, should initially undergo bioburden reduction. So they will have to be sterilized. They will have to be put back into the system before we conduct the VHP of the isolator. We get a lot of 483s from the FDAs, a lot of warning letters. Even, you must have heard about them, and you must have also seen some of the warning letters coming in from the regulators. And most of the warning letters are pertaining to the aseptic operations and the lacunas in the aseptic and performing the aseptic operations. So here I have listed down some of the points, like during the aseptic filling of vial, the operator used restricted access barrier system to remove a jammed stopper by reaching over the exposed sterile stoppers in the stopper bowl. So when you're going to do any manipulations in the critical areas, basically your hand is going to move above the objects which have been pre-sterilized, and by doing that, maybe it's like your glove can also touch the objects, making it non-sterile. As you know, for any one batch which you manufacture in your injectable facility, only 60 vials are taken for the sterility testing. So it's like even your batch size is 1 lakh, 5 lakh, 2 lakh, 3 lakh number of units, you have a very small portion going for the sterility testing, and based on that the entire batch is released. So the concept of sterility assurance at each and every stage of manufacturing is of a great importance, because then the type of operations that you're going to carry out and the type of manipulations that you're going to do, whether it is going to affect the sterility of the product, that is what we have to seriously think, and we have to validate such type of systems in order to not to have any occurrence again. Or the operator leaving the door of the wrap system open for a long period of time, and then there was no justification, which again came as a 483. or basically I've seen in some cases wherein the lyophilizer operation in most cases wherein it is a manual operation where you're going to, put the vials into the tray, which are partially stoppered. And then the operator under the laminar is going to transfer them into the shelf of the lyo. This is a very risky operation because basically the vials are exposed. When you're going to lift the tray or when you're going to, stack the vials into the tray, invariably you are going to touch the vials. You are going to touch the vials which are on the sides, and you are also going to, have a lot of issues in terms of sterility failures, because it's like the operator may not know, and it's like it will be very difficult for you to train the operator to carry out in a proper way, because there is no proper way when this is going to be a completely a manual operation. The operator passing a pen directly over the stopper board to another person. Yes, again, this was like, some of the FDA warning points coming in as 483s. So with this, now we come to isolator design, how we are going to design an isolator. And during the isolator design, this is normally what we have seen when we are talking to the customers, that basically, they have a lot of questions, because many of the customers who are going in for the first time for the isolator design may not have a complete idea as to how it has to be designed and what type of precautions and what type of RTPs, how we have to do it. So basically, when we talk about the mock-up design, so if we look at the complete process of coming up to this particular stage, because the mock-up design is going to happen when you already have a PO issued to the supplier, and you have given the PO and you have paid the advance and basically given him all the technical specifications signed copy. The first thing the supplier is going to do is he is going to make a mock-up. Why this mock-up will be required? Why you require a mock-up? The simple reason for this particular mock-up is, before the PO, you were all talking about the technical points that you want to do this. This is a machine. This is how the vials are going to get transferred. This is how I'm going to put the environmental plates inside. And, it's like, this will be the points for the viable. This will be the points for the non-viable monitoring. And these are the points wherein I'm going to take the reject vials out. And there is an IPC system on my machine, which will be, automatically doing the tear weight and the final weight, and the vials which I have to take it at a particular interval, which I want to do it outside for the testing of the fill volume. I'll be taking it through the RTP. So when we were just discussing this particular point in order to finalize the design for an isolator, we were not having any idea as to, at what location this particular ports will be required, at what locations the gloves will be coming in, what will be the height of the gloves. So the height of the glove will depend upon the operator's height. So the operator should be very comfortable, in putting his hand through this particular glove port and doing the intervention inside the critical areas. So he should have that particular height for, doing the manual intervention. Otherwise, he will not be able to reach inside the isolator or inside the glove port. In order to do all this, basically, the first thing after the PO is, the mock or a wooden model of an isolator is made. And that wooden model of an isolator is going to actually show how you are going to do the operations, how you are going to take the material in, where the material is going to be placed, or where you require the hangers to be placed to hang the plates or to hang the material which you are going to take. You can see in another slide, I will be running a video. It's a very short video, which will show you how this particular mock is being carried out. So basically, when we look at the mock, you can see that there are certain areas inside the machine where you can see on the right hand side, there is a Caesar which is hanging from the hangers. And there are some settle plates which are also hanging from the top. And you have to, simulate with the help of a mock, that these are the areas with the help of a glove port or with the help of an RTP, you will be able to reach. So you can just have a look at the video. So now these are the settle plates or the plates which he wants to expose inside, which have been put on the hangers. He'll be taking a knife, scissors. We'll be removing it. So basically, we are checking whether for the operator, it is very convenient for him to operate and do the MS for the continuous viable monitoring. So this mock test is very important before we actually go with the final design, because all the points, including the position of the RTPs, how many RTPs you require, how many glow ports you require, where the location of the viable and the non-viable has to be on the entire integrated line. Everything gets finalized, including the design for the hangers and everything. Okay. So apart from this, there are other design criteria which are going to be the RTPs, the rapid transfer airlocks or the rapid transfer ports, wherein the tools, the media parts, the autoclave parts will get transferred. So how the design has to be, how you have to do the alpha beta interlocking, how you have to transfer the material, everything is going to get defined when you are going to define this particular ports onto the machine. These are the rapid transfer port. You can see some of the pictures wherein the material is getting transferred through the rapid transfer port without breaching the integrity of an isolator and without causing any contamination inside an isolator. So as the audience, they have worked more on the isolator line, you must have definitely experienced on this rapid transfer ports and the transfer systems that is associated with the isolator. So even when you are going to take the settle plates inside for the environmental monitoring, you are going to take it through the biosafe or you're going to take it through the RTPs, and that will be stacked inside or it will be hanged inside an isolator before you do the VHP sterilization. Because normally when you do the VHP sterilization, the way you are going to hang the material inside, it is very important for you to demonstrate that, because there has to be a gap between the article wherein this particular vapor hydrogen peroxide is going to get circulated in order to have a 6-log endotoxin reduction. This is going to be the design for the mouse holes that you are going to have. This is again, as I was saying, for the vial filling line, you will be having from after the filling, the vials getting transferred to another zone, which is going to get, transferred to maybe a lyophilizer chamber. So there will be a conveyor, there will be a isolator chamber on top of that. And between these two particular isolator chambers, there will be a mouse hole. So the design of the mouse hole is very, very important in order to maintain the proper overpressure. And as you can see over here, it has got the inflatable gaskets wherein this particular cover is going to sit when you are going to do the VHP sterilization. Normally, when you have an integrated vial line, one vial line with a lyophilizer system, if we have to talk of, it can connect to one vial lyophilizer system. It can also connect in series to 4 lyophilizers in series with the help of a row by row system, which is making it is forming a combing device for the vials in front of the chamber table. And at the constant loading height, when the shelves are going to collapse, you are going to push the vials onto the shelf for doing the lyophilization activity. So basically, when you have one or more than one of this particular chambers getting connected, it becomes a very complex system for an isolator, because on the same vial filling line, you will also be doing the liquid filling one day, And maybe on the next day, you are going to fill the lyophilized product, which you are going to put it in the lyophilizer. So when you make the design for the lyophilization system, maybe the lyophilizer chamber will be getting divided into 3-4 different chambers, having their own independent air handling systems. So your VHP sterilization, you can do it for all the 4 chambers using this particular 4 areas. Or if you feel that if your lyophilizer is in right angles and your vial sealing machine is linear to your filling line, basically when you are doing the liquid product, you may not require to do the VHP of the lyophilizer isolator. And in that particular case, as you can see, the conveyors can be retracted. The conveyors, they are the retractable conveyors. So the conveyors will be taken inside the chamber. The chamber will be sealed off. And basically you will be doing the VHP of this particular chamber. If this chamber, the other chamber, which is in right angles and not required to be VHP sterilized because we are not going to do the lyophilized product on that particular day, we can close that chamber and do the VHP whenever the VHP is required, when before loading that vials or before unloading the vials from the lyophilizer. So when we talk about the mouse hole design is the most important design, because it has to be as small as possible so that we can maintain the overpressure, and at the same time it has to be properly VHP sterilized. The inner surface of this particular mouse hole has to be properly VHP sterilized. So you will have to design a proper, the enclosures or the closures for this particular mouse holes. In case of a liquid transfer, you're also going to work with the SAT connectors. Now, when we talk about the SAT connectors are basically for the connections for the sterile liquid into the sterile final filling environment. It will be pushing it from the outside area. When it comes through the isolator, it will be having an external port, which is of SS316L. It will be having an internal port, and it will be having a disposable connection device, which is called as a gamma SAT. So this SAT is, of course, from Millipore, and the system is integrated in such a way, and it has been interlocked in such a way that by mistake also this gamma SAT or the disposable part should not get removed when you are trying to do the aseptic connections inside an isolator. So this is how you are going to connect the liquid from the outside area into the isolator chamber. Again, when we are talking about the liquid aseptic transfer, we can also use the single-use technology. So here you can see on the left-hand side the picture, which is showing the heads of the peristatic pump. Now, when we are talking about the heads of the peristatic pump, in some cases, the customer requires them to be installed outside the machine area. In some cases, they are also installed inside the machine area. Now, this particular video, which I'm going to run, will show you basically how this particular connections with the single-use technology you can do for the isolator. So after this, there will be a video which will show you exactly how the connections are being done. we are running short of time, I think so I'll have to little bit speed up. Okay. So now coming to the WIP and the vapor hydrogen peroxide decontamination. So basically here, for the wrap system, the cleanliness process prior to the disinfection step is essential. Any residue that remains may inhibit the effectiveness of the decontamination process. So that is coming as a cGMP annex draft. And if you see the spray ball, even these are the videos which I'll quickly run now. So you can see there are spray balls inside the chamber. And here, basically, even for the ducts, which are the return risers, basically, there are spray balls in the risers. So when you're handling a potent product, you can also clean this particular, risers with the help of the spray balls. Sorry. When we are talking about the water at the base frame, which has to get removed, all the isolators, when we are talking about the isolators, they are all been interconnected for the drain points, and the bottom plate will be having the drain, and it is already sloped towards the drain point where the water will get removed. So normally when we talk about an isolator system, isolators are, there has been a lot of improvement in the isolator in past 40 years in terms of its control, ergonomics, cycle time, load time, as well as the cost, as I said. And for the sanitization of the isolators, the vapor hydrogen peroxide is found to be very, very effective because it is easily available. It is less toxic compared to the other gases. What are the other gases that you can use? People are also, having ethylene oxide, nitrogen dioxide, or chlorine dioxide, which can be used as, for the sanitization. But in terms of, the application, vapor hydrogen peroxide, as it is easily available, it is less toxic. Finally, when it comes, it leaves no residue. It basically gets converted into water and oxygen. So it is widely used in the sterile isolators for doing the sanitization of the isolators. So normally, the vapor hydrogen peroxide is 30 to 35% liquid hydrogen peroxide, and it has got a boiling point somewhere around 108 degrees. It is heated to a temperature of around 110 degrees, and it evaporates into hydrogen peroxide and water. And when it is introduced in the chamber, you have to have the control of the temperature as well as the humidity inside the chamber. So basically, the temperature will be controlled at around, say, 25 to 27 degrees inside the chamber, and the humidity will be less than 45% RH. And you go for a lower humidity in the chamber, because in the chamber, when H2O2 and water, they are in the equilibrium phase, that is between the gaseous and the liquid phase, it will be totally dependent upon the temperature that is, are present inside the chamber. So the H2O2 will be present on the surface in a micro condensation with water, and it will be having an effective sanitization due to its liquid phase hydrogen peroxide. Any decrease in temperature or any increase in RH will lead to a condensation, which can reduce the effectiveness of vapor hydrogen peroxide. So basically, this is going to be the parameter on which the vapor hydrogen peroxide is going to inactivate. It inactivates the cells, and thereby makes the cell, or it makes it non-toxic, or it does not have any activity. This will be the cycle phases of the VHP cycle. So there are 4 phases. The first phase is called as a conditioning phase, where the initial RH is less than 45. The temperature is also maintained, and the evaporator is preheated to temperature, which is going to, have this particular vapor hydrogen peroxide being pumped inside the chamber. So in order to ensure the reproducibility, the initial condition should always be the same, not only for the key parameters, but also for the loading parameters. So whatever loadings that you have inside the isolator, they have to be consistent every time in order to have the consistent results of the VHP. So in the gassing phase, as you can see, the temperature, now you can see this is a RH, just using my mouse. So in the conditioning phase, you have gone for the lower RH, and then you have started, heating, and you have started putting in the VHP inside the chamber. As soon as the VHP starts entering the chamber, even the humidity part will start increasing, and it will increase, and there will be a peristaltic pump which will be controlling the flow of the vapor hydrogen peroxide or the liquid hydrogen peroxide into the evaporator chamber. Evaporator chamber will evaporate, and it will be putting the vapors inside the chamber. So basically, there will be a fixed amount of dosing that will be happening inside the chamber, which will be controlled with the help of a sensor. So the sensor will sense what is the amount of VHP that you are putting inside the chamber, and that will be controlling, the dosing of the VHP into the chamber. So once the gassing phase is over, we come to the decontamination phase, wherein you can say here, basically the heaters, they are running at a constant temperature. The humidity inside the chamber has increased, and now it has gone to a plateau wherein it is flat. And basically this is the phase where there is a maximum moisture inside the chamber. There is a injection of VHP happening inside the chamber, and this will be done till the time you have a 6 log spore reduction, which is achieved on surface of direct or indirect contact surface inside the isolator. So once your decontamination phase is over, it will go for the next phase, which will be called as the aeration phase, wherein a large volume of new air will be introduced inside the chamber. And here you can see it has started going downwards. The curve will start going downwards. This will be the air which will be replacing the VHP which is there inside the chamber, and the VHP will be going through the exhaust. With the help of a catalyst filter, it will get neutralized. So this is how the VHP phase runs. And in order to have a proper science-based protocol for the VHP and to fully understand, we will have to have the parameters controlled, which are environment, which are generator design. It is the results caused by the other conditions such as the chamber conditions, chamber temperature or humidity, gas phase concentration, liquid phase condensation, as well as the process control, wherein all these parameters are going to be very, very important for you to have a proper validated cycle for the vapor hydrogen peroxide. In terms of BIs and CIs, which you are going to keep as per the matrix inside the chamber, and that can be also defined based on the difficult to reach areas for the VHP, wherein you are going to place the BIs and CIs. Normally, the BIs takes around 7 days for you to get the reports. So nowadays, the enzyme indicators are also available, and the enzyme indicators will give you the results immediately. So when you are doing the cycle validation, it is always better that you also do the cycle validation using the enzyme indicators, which will give you a faster results, and you will be able to take a call based on the validation parameters. Now coming to the last chapter of this particular presentation, how to validate. So you will be going with a typical QPP, wherein the critical quality attributes are going to get listed on the left hand side, and you will be having the URS, which will be the first document which you are going to make, and the URS has to be exhaustive. It should take into consideration the process and all the parameters that you're going to handle and the operations that you're going to handle in isolator. Because the isolator design and the isolator controls, everything will have to be properly defined as to what type of levels that you want to achieve. So after the URS, you are going to make the functional specification, functional descriptions, the hardware and the software design specifications, and then you will be making a DQ, which will be a design qualification. And that design qualification will have to be signed by both, that is by the supplier as well as by the customer, which clearly says that, yes, now this is how the isolated design is going to happen. So basically, once you sign this particular design qualification document, this is what is going to get verified at the time of FAT or a factory acceptance test. So once the DQ is signed off, basically then the construction of the machine starts. And then the first test that you are going to conduct, that is a customer going to the supplier side because the equipment is still with the supplier, is going to be the FAT. So during the FAT or the factory acceptance test, you are going to check the complete DQ and you are going to verify that each and every point of the DQ and the makes and the models and the calibration range, everything has been specified. And you have the same, the numbers which are specified in DQ are appearing also in FAT. And you are also going to carry out certain operational qualification tests at the supplier end, which we call it as a critical test. So maybe in operational qualification, if there are more than 20-30 tests that you are going to have, you will be conducting some of the tests which are very, very critical with respect to the operation or with respect to the working of this particular isolator. Once the FAT is completed and you have any open points in the FAT, normally this FAT points are given to the supplier. The supplier will work on this particular point. He will try to rectify and he will try to give another FAT with all the points included. And once the customer is satisfied, the machine is dispatched from the premises of the supplier. And when it arrives on site, it is installed on the machine, installed in the place. And then before the operational qualification, we are going to conduct the site acceptance testing, which is again is going to be a part of IQ. It is going to be a part of OQ, which you are going to conduct, which is somewhat in between IQ and OQ. So you are going to do a pre-OQ just to confirm that all the parameters which you want to run on the machine on the isolator, they are as per the parameters that have already been defined and signed off. And then you will be, completing the IQ-OQ validation and finally the performance qualification validation. So this is going to be the, the complete verification process or the process which you are going to carry out right from the making of URS to the finalizing of the PQ. In terms of qualifications, I have listed down some of the qualification parts. So basically the test instrument qualification, there will be some test instrument which are the instruments, the equipments which will be having the calibration certificate coming in from the supplier side. So at the time of the machine getting manufactured at the supplier end, you will be referring to this particular calibration certificate. But once the machine is shipped to your premises, it is going to travel by sea and it will be having a longer time traveling, and then basically there will be a lot of loading, unloading happening at the docks, at your premises, at the supplier premises. So maybe some of the instruments, though they are still in the calibration range, may go out of calibration. So it is always better that once you have the machine installed at your premises, before you conduct the OQ, you conduct the complete calibration of the critical gauges and the instruments which are there on the machine in order not to have wrong results during the operational phase. So document qualification, FAT, SAT, IQ, installation check, it will be done during the FAT, SAT and IQ. Main component check, again, you do it at the same time. Critical material certificate, critical surface finishes, you're doing it at the time of FAT, instrument calibration check, then pressure differential, air velocity control, leak test. So these are all the parameters, I think. So you'll be having a copy of this in PDF format. So maybe you can also run through this particular list. In case of a qualification which is for the computerized system, so normally everybody is using 21 CFR Part 11 compliant software, Windows 10, Windows 11 compliant. So basically all this software and the software validation protocol, whether as per GAM5 or whether as per 21 CFR Part 11, you'll have to have a proper protocols. You'll have to have the control system qualification, input output devices, clock calibration, automatic logout time test, HMI navigational test. All this particular test has to be demonstrated during the qualification of the computerized system. So these are some of the photographs and the schedules that we have given, that is for the site installation. So this is how the equipment arrives on site. And basically you can see on the right hand side, the technicians are trying to put leveling of this particular isolator. They are putting this particular isolator in place. And as you can see on top, you do not have a false ceiling. So once the machine is put in place, then the false ceiling is done on top of the machine. And this is how the ducting and the duct and as well as the HVAC system, the connections to that, everything will be done. And this is on the left hand side, you can see it's a semi-finished isolator, and on the right hand side you can see the completely finished isolator with the background area as grade C in the clean room. So with this, I come to an end of this particular presentation. I thank you everyone, and now I hand over to the technical team who will be answering all the questions from your side. So thanks once again. Thank you very much.
Thank you, Sanjeev. That was a very detailed and comprehensive session. Thank you very much for that. Now we have 3 minutes left of this session, and I know that the team from Toflon, both Yenlu and Asha, have been busy answering your questions that you've posted on the chat. Please do continue to post questions on the chat so that they can answer your queries directly. And after this session, as long as we have your contact details, we would be happy to provide the follow-up for you so that you can continue the discussion. Yenlu, do you want to answer any specific question, or does anyone would anyone like to unmute and ask a pressing question? No, it sounds like we're good. Just mentioned earlier, for those people who came in later, the presentation will be sent to you as a PDF after the session, and our recording of this session can be found on the ISPE Singapore affiliate YouTube page. So you can re-watch it and catch the bits that you didn't see at the beginning, if you like. Unless there's any other questions, Yenlu, Asha, do you have any other comments?
No, from my side. I think Asha is answered most of the question by the audience.
Yeah, thank you. And if you want to put in any additional questions, please do so now. We will keep a record of the log and pass the questions on to the team for you. And also their details will be provided on the email. There were quite a few people who have come in as guests whose details we don't seem to have. And if your names are not recognizable and you know that you haven't previously registered, please do put your detail in the chat for us so that we can send you the PDF after the presentation. So I think that's all we have for now, and we are at the 6:30 mark. So we'd like to thank everybody for joining this session. We'd like to welcome you to come to our August conference. And that will be on the 18th to 19th at Suntec. Toflon will be exhibiting at the show. So they will be there to answer your questions and to meet up with you personally, along with 40 plus other exhibitors. So please do join our conference if you have a chance, whether that's online or in person. And that's www.ispesingapore.org. With that, I'd like to thank our speaker, Sanjeev, and the team at Toflon, and to thank all of you for your participation this afternoon. And we wish you a very good evening or afternoon or whatever that is in your time zone. So thank you all, and take care. Goodbye.
Thank you. Thanks, everybody. Thank you very much.